Hi everyone, welcome to our series on vectors. This is episode 1 on the intro to vectors, and we'll be exploring basic properties and using operations with vectors. So in episode 0, the big picture, we learned that a vector quantity is solely defined by its magnitude and direction. This means that we can have a lot of vectors with the same length and the same direction, but they are all called equivalent vectors. So it doesn't matter where the vector starts or where it ends, but it only depends on how long and in which direction it's facing. But the vector that starts from or has its tail at the origin is called the position vector, since it tells us the position of the vector relative to the origin. We also prefer drawing and calculating vectors from the origin, so the position vector proves very useful. So in this episode, we'll be investigating 3 different topics. 1. Vector properties. 2. Vector addition and subtraction. And 3. The dot products. Now that we know what a vector is, it is important to understand the properties of vectors so that we can use them appropriately. A vector can be represented by a directed line segment or simply an arrow. The vector can be denoted by a bolded letter, but in practice, it's going to be hard trying to bold a letter, so it's preferred to label vectors with a squiggly line underneath called a tilde. The magnitude of a vector is denoted with absolute value symbols, as absolute values extract the magnitude. The direction of a vector is usually represented by the anti-clockwise angle from the positive x-axis to the vector. We can also represent a vector based on the 2 points where the vector starts, its tail, to where it ends, its head. For example, this is vector PQ. Now let's discover what scalar multiplication means. It sounds fancy, but it just means you can multiply a scalar quantity like a constant and transform the vector. So if we multiply a vector by a positive constant greater than 1, this would stretch the vector by a factor of that constant, but maintain that same direction. If we multiply by a positive constant less than 1, this will shrink the vector. And finally, if we negate a vector, this means that the direction is reversed while the magnitude remains the same. A zero vector is a directed line segment from a point to the exact same point. It has no length or no direction, so it can be represented by a dot. Fun fact: if we multiply 0 to any vector, we will just get the 0 vector. Finally, let's define a unit vector of vector A, labeled as a hat. The unit vector is just a vector A with the same direction but a length of 1 unit. So we can derive the formula by just dividing off the length of the vector from the original vector A. So rather than just labeling vectors with letters, we want a standardized and consistent way to label all vectors relative to each other. Because they all lie on the 2D Cartesian plane, we can break down each vector in terms of their horizontal and vertical components. The I vector is the unit horizontal vector, and the J vector is the unit vertical vector. These are called the basis vectors as they define the dimensions of the 2D plane. So each vector can be written in the unit vector form, which requires the number of horizontal and vertical unit vectors to build the original vector. Hence, every vector in the universe can be resolved into a sum of the scalar multiplication of vector I and vector j. We can also express vectors as column vectors, where the top number represents the number of horizontal unit vectors and the bottom number represents the number of vertical unit vectors. Column vectors are so much easier to use, especially in calculations, so watch out. Now, using Pythagoras' theorem, we can find the length of a vector as square root of x squared plus y squared. And using basic trigonometry, we can deduce the direction of a vector as tan inverse y on x. Just be careful of the quadrants when looking for theta. Now that we know the basic properties of vectors, let's try to understand how to use mathematical operations with vectors. Like, what does it even mean to add vectors? We are already used to adding scalar quantities like 3 plus 3 is equal to 6. But how do we add vectors which are just arrows? Let's try to understand vector addition visually. First, draw the position vectors of A and B. We are adding vector B onto vector A, so we draw an equivalent vector B at the head of vector A so that we can continue on the journey. The final addition vector is the vector that joins the first tail to the last head together. To help us better understand vector addition, we just say add the head to tail. Also, note that once we draw all the position and equivalent vectors, the addition vector represents the diagonal of the parallelogram that starts from the origin. Now, algebraically, it's even simpler. When we add two vectors together, we just add the horizontal and vertical components separately. So we don't know how to subtract vectors yet, but we do know what a negated vector is. So an easy way to understand vector subtraction is to transform it into a vector addition by negating vector b. Now we just follow the same steps and add head to tail and extract the final subtraction vector. Let's translate the vector and draw an equivalent subtraction vector at the head of vector A. We can observe that the subtraction vector is the other diagonal of the parallelogram joining the heads of the position vectors. A useful way to memorize the direction of vector A minus B is 2A from B. Similarly, what does it even mean to multiply vectors? How can we multiply vectors when they're just arrows? The simple answer is that we can't use the standard multiplication. But in vector analysis written by Edwin Wilson, founded upon the lectures of Josiah Gibbs, a concept called the dot product was introduced. The dot product of vectors is written with a dot, so make sure you try not to use the times symbol. The dot product of vector A and vector B is the length of A times by the length of B times by the cosine of the angle between the two vectors. And the interesting thing is that the dot product of two vectors is equal to a scalar quantity. In rearranging, we can derive something called the direction cosine by calculating the dot product of the unit vectors of A and B. Now, through the application of cosine rule using vectors, we can derive another expression of the dot product. It's just equal to the product of the horizontal and vertical components together. So in column vector form, just multiply the top plus multiply the bottom. Now we will conclude with properties or axioms you can use with vectors. Vector addition and subtraction is commutative, which means you can add forwards and backwards. It's also associative, which means that you can add or subtract in a different order. Scalar multiplication is distributive, which means that you can expand the brackets and distribute each term. Similarly and surprisingly, the dot product is also distributive. So that's it for episode number 1. We have introduced you to the world of vectors by going through all the properties and operations you can perform. So tune in to our next episode on projections and further applications of vectors in various questions. So like, subscribe, and leave a comment below on what you would like to learn in the future. I'll be there.